Hello, hope you had a great start for 2021. This is Yahya Saddiq, iOS Tech Lead at Voice. Voice is a tech company. With my team, we co-develop with overseas engineers building frameworks and common app for Vodafone local markets. On a personal level, I'm a father of two, fitness enthusiast, knowledge sharing and coding are my passion. Today, I'll talk about Swift memory management and how to debug memory issues, specifically leaks and retain cycles. In the beginning, we'll talk briefly about heap and stack memory regions. Afterward, we'll demonstrate the class lifecycle, reference counting, and class deinitialization. Then I'll dig deep into reference cycle in both class enclosures, causes of memory leaks, and how to break them. You might see the reference cycle called the retain cycle in books and online resources. They refer to the same thing, so don't worry about it. Before the end, I'll use a demo app to show you memory leaks using the Xcode Memory Debugger. And finally, we'll go through a few tips on how to eliminate memory bugs. Both the heap and the stack have essential roles in the execution of any program. A general understanding of what they are and how they work will help you visualize the functional differences between a class and a struct, and how you should utilize memory usage. A stack is strictly organized and tightly managed and optimized by the CPU. It's very efficient and fast. The system uses the stack to store anything on the immediate thread of execution. On the other hand, heap doesn't organize data. It just leaves everything scattered around in a loose pile. The heap is generally a large pool of memory from which the system can request and dynamically allocate blocks of memory. The system uses the heap to store instances of reference types such as a class and closure. The heap doesn't automatically destroy its data like the stack does. Additional work is required to do that. This makes creating and removing data on the heap a slower process compared to on the stack. In Swift, a struct is a value type, which stores the actual value and provides direct access to it, while classes are reference types. So a variable of a class type doesn't store an actual instance. It stores a reference to a location in memory that stores that instance. Let's assume we have an author class and a person struct. In memory, a person variable would not reference a place in memory, but the value would instead belong to person exclusively. A new variable for the same value will copy an assignment and take a new place in the stack. As you can see, the heap is not touched so far. An instance of author class will create an object in the heap and store its address in the stack. A new variable for the same reference type instance will hold the same address and point to the same place in memory. So far, we know that objects are created in memory and that they are stored on the heap. But objects on the heap are not automatically destroyed because the heap is simply a giant pool of scattered memory. Without the utility of the call stack, there is no automatic way for a process to know that a piece of memory will no longer be in use. In Swift, the mechanism for deciding when to clean up unused objects on the heap is known as reference counting. In short, each object has a reference count that's incremented for each constant or variable with a reference to that object, and decremented each time a reference is removed. When a reference count reaches 0, that means the object is now abandoned since nothing in the system holds a reference to it. When that happens, Swift will clean up the object and marks the memory as free. Now, creating another author for the same author instance increment reference count to 2. Creating lots of author array for same author instance incremented to 5. Discarding another author decrementing to 4. Discarding lots of author elements decremented to 1. Assigning a new author object to the original author variable decrements the original author object to 0. Mark its memory block as free and creates a new author object with a ref count equal 1. In this example, we don't have to do any work ourselves to increase or decrease the object's reference count. That's because Swift has a feature known as automatic reference counting. While some older languages require you to increment and decrement reference count in your code, the Swift compiler adds these automatically at compile time. This principle of reference counting mostly applies to classes, because when you pass around an instance of a class in your code, you are really passing around a memory reference, which means that multiple objects point to the same memory address. When you are passing around the value types, the value copied when it's passed around. This means that the retain count for a value type is typically always 1. There's never more than one object pointing to the same address of a value type. If you use a low-level language like C, you're required to manually free memory you are no longer using yourself. Higher-level languages like Java and C# use something called garbage collection. In that case, the runtime of the language will search your process for references to objects before cleaning up those that are no longer in use. Garbage collection, while more powerful than ARC, comes with memory utilization and performance costs that Apple decided was not acceptable for mobile devices or general systems language. When an object reference count reaches 0, Swift calls the initializer before removing an object from memory. Much like init is a special method in class initialization, dinit is a special method that handles the initialization. But unlike init, dinit is not required and is automatically invoked by Swift. You also are not required to override it or call super within it. Swift will make sure to call each class the initializer. What you do in a deinitializer is up to you, because an instance is not deallocated until after its deinitializer is called. A deinitializer can access all properties of the instance it's called on, and can modify its behavior based on those properties, such as cleaning up other resources, save state to a disk, or execute any other logic you might want when an object goes out of scope. Now, let's intentionally create a reference cycle, assuming we have 3 different classes, author, book, and editor. Both the author and the editor have their list of books, and the book is linked to an author and editor. Let's create an author Mustafa Mahmoud, great Egyptian doctor, philosopher, and author, a book dialogue with an atheist for the author, a nice book to read by the way, an editor Wali, assign an editor to the book, add the book to the editor's list of books, and add the book to author's list of books too. A typical publishing house data model. Then, let's put them all in a scope so that as soon as they go out of scope, the reference to them should drop and they should be deallocated. The problem here is that at the end of scope, the reference of book, editor, and author never drop and reach 0. Why? Because book and author have a reference to each other, and each instance keeps the other one alive, same as for book and editor. And we made things worse by ending the scope. The stack list items will be deallocated, and there are no more references to the initial objects. This is a classic case of a reference cycle, which leads to a software bug known as memory leak. With a memory leak, memory is not freed up even though its practical life cycle has ended. Reference cycles are the most common cause of memory leaks. Key point here is that automatic reference counting handles reference counting for you automatically. But it's important to you to watch out for reference cycles. We all create leaks at some point, from junior to senior engineers. It doesn't matter how experienced we are. It's paramount to eliminate them to have a clean and crash-free application. Why? Because they are dangerous. They might not appear until the program has been running a long time. A memory leak is often like a slow leak in a car tire. Leave it a few hours and there's no sign of problem. Leave it a week and your car is grounded. So guys, Don't forget to check your cards at the end of the meetup. Memory leaks cause two major problems. First, memory footprint, where a direct consequence is objects not being released. Those objects are actually garbage. As the action that create those objects are repeated, the occupied memory will grow. The other problem is side effects. Imagine an object that starts listening to a notification when it's created inside init. It reacts to it, altering the database, playing a video, or posting events to an analytics engine. Since the object needs to be balanced, we make it stop listening to the notification when it's released inside the dinit. If this object leaked, dinit is not called. It will never die and will never stop listening to the notification. Each time the notification is posted, the object will react to it. If the user repeats the action that creates the object in question, there will be multiple instances alive. All those instances responding to the notification and stepping into each other. In these cases, you gotta wish for a crash. Leaks may come from third-party SDK or framework, for example, even from classes created by Apple II, like CA layer or UI label. In those cases, there is not much we can do, except waiting for an update or discarding the SDK. It's time to break the reference cycles before they break us. First, a book doesn't always assign to an editor, so it makes sense to model it as optional type. And the book doesn't own the editor, so it makes perfect sense to make it a weak reference as well. Weak means the reference in this variable will not take part in reference counting. When a reference is not weak, it's called a strong reference, which is the default in Swift. The great thing about using weak variables is that they automatically detect when the underlying object has gone away. This is why they are always declared with an optional type. They become nil once the reference count reaches 0. There is another means to break reference cycles, unowned references, which behave much like weak in that they don't change the object's reference count. Unlike weak references, however, they always expect to have a value. You can declare them as optionals. Think of it this way. A book cannot exist without an author. At the same time, a book doesn't own the author. Therefore, the reference should be unowned. Here, you guarantee that a book always has an author, hence author is not declared as optional. And a book can have an editor at certain time, hence editor is declared as optional. On the other hand, books is a variable, so it can be modified after initialization. Voila, our code breaks the reference cycle with the weak and unowned keywords. All the dinit methods run and they will be deallocated. Closure is simply a function with no name. You can assign it to a variable and can be passed around like any other value. They are named closures because they have the ability to close over the variables and constants within the closure's own scope. This simply means that a closure can access, store, and manipulate the value of any variable or constant from the surrounding context. The variables and constants used within the body of a closure are said to have been captured by the closure. And because Swift is a safe language, closures extend the lifetime of any object they use in order to guarantee that those objects are alive and valid. This automatic safety is nice, but the downside of this is you can unintentionally create a reference cycle if you extend the lifetime of an object that itself captures the closure. Let's see that in an example. For example, if we add a lazy property that computes book's description for the book class. When we call the description in our scope, the book object creates a block of memory for the description and holds its reference. At the same time, description strongly captures self through title and author, which in turn increases the reference count for the book object. Here we have a strong reference cycle between the book and the description. At the end of a scope, only the author's deinit method runs. To break the cycle, we'll need to know about a language feature called capture list. Capture list is a language feature to help you control exactly how a closure extends the lifetime of the objects it refers to. Simply, there are a list of variables captured by a closure. Since the closure shouldn't exist after you release the book object from memory, self will never be nil, so we can change the strong reference to an unowned one using a capture list. No more reference cycle. There are certain times when you can't capture self as an unowned reference, because self might become nil, and the app will crash for reading a nil object. Weak self means that the closure will not extend the lifetime of self. If the underlying object representing self goes away, it gets set to nil. The app won't crash if self goes away, but does generate a string interpolation warning, which you can fix by the strong weak pattern. The strong weak pattern does not extend the lifetime of self, but converts the weak reference to a strong one after it enters the closure. So it's guaranteed to live until the end of the closure. You can print a suitable message if self is nil this time, and the warning will disappear. Finally, time to show you reference cycles using Xcode Memory Debugger. Now let's go and buy a book. The demo app is a single view with a table view app. It contains a single book data stub with the publishing house model we have seen earlier. Let's give it a run. For demo purposes, table reloads data with new instances of the same book contents on pull to refresh. Apple introduced the new visual memory debugger in Xcode 8. Even better is that you use it directly from the Xcode debugger, so you don't need to use instruments. You can open it by clicking on the Debug Memory Graph icon. The memory debugger breaks execution of the app and builds a visualization of memory usage at that specific time. Note that this might take a little while depending on how big your app is. The navigator window shows the object created on the heap, organized by type and instance. When you select an object in the navigator, the middle section will show you the memory graph of the selected object and the relationships it has to other objects. Sometimes it's a big graph, other times it's a smaller graph with just a couple of objects. The memory inspector on the right side shows details such as the size, class hierarchy, and allocation backtrace. It can help you to use the control at the bottom of the navigator to filter the type you are looking for. If Xcode spots a relationship that it suspects to be a memory leak or retain cycle, it will add a purple square with an exclamation mark behind the object in the sidebar. Awesome, memory doesn't show any leaks so far. Now let's unpause the app and release the current book object by reloading the table data. Now, let's open the memory graph again. Oops, something's leaking. The previous book's neither author objects have been released. Let's filter leaked objects only. Of course, this happens because of the reference cycle with author, where book is strongly holding author, and the same with author. And the more pull to refresh we make, the more leaks the memory will have until it reaches the crash moment. That's all for Xcode Memory Graph. Give it a try the next time before creating pull request. 3 final tips. 1. Have a strong code style defined for your project and respected. 2. Use SwiftLint. It's a great tool to detect early issues at compile time. 3. Profile the app frequently using Xcode Memory Debugger. You, as a mobile software engineer, always should be conscious of your app's memory footprint. It's highly recommended to check your app memory usage before delivering a fix or a new feature for your app or framework. You should be conscious to avoid retain cycles and memory leaks, which are major memory-related issues. that cause unwanted side effects, bad user experience, and crashes. Thank you all for attending First Cockleheads Berlin in 2021. Wish you a free of leaks year. Bye bye.